Hello everyone, today we will learn about the engineering construction of the drainage consolidation preloading method. The main knowledge points for this section include 1. Definition of the drainage consolidation preloading method. 2. Surcharge preloading method. 3. Vacuum preloading method. 4. Quality inspection. Here, let's review the knowledge points we studied earlier. Do you remember the dynamic consolidation? How does it differ from the drainage consolidation preloading method we are studying today? First, let's understand the definition of drainage consolidation preloading method. The drainage consolidation preloading method is a technique applied to natural foundations or foundations with pre-installed vertical and horizontal drainage elements, such as sand drains, sandbag drains, or plastic drainage strips. The method uses the weight of the structure itself for stepwise, gradual loading, or applies preloading on-site. Before construction, this process allows poor water in the soil to drain, gradually consolidating the foundation and causing settlement, while the soil strength increases over time. The preloading method includes surcharge preloading and vacuum preloading, and it is suitable for saturated, cohesive soils, such as muddy soil, silt, and reclaimed fill soil. Here is a system diagram of the drainage consolidation method. Next, let's introduce surcharge preloading method. Surcharge preloading refers to applying a load on a saturated soft foundation, causing pore water to slowly drain, reducing the pore volume, and resulting in consolidation deformation, increasing soil density and strength. The surcharge preloading method consists of a loading system and a drainage system. According to construction requirements, it can be divided into self-weight preloading, applied preloading, and water-loaded preloading. According to the loading procedure, it can be classified as single-stage loading and multi-stage loading. Please look at the figure. The key construction points of the surcharge preloading method include: ensure that the performance indicators of plastic drainage strips meet design requirements, and that they are properly protected on-site to prevent damage from sunlight or contamination, with any damaged or contaminated strips being unusable. The sand filling in sand drains should be calculated based on the borehole volume and the dry density of medium-dense sand with the actual fill, not less than 95% of the calculated value, and the dry sand should be used in sandbags, filled to a compact state. Equipment capable of measuring depths must be provided during the installation of plastic drainage strips and sandbag drains, and the sleeves used for plastic drainage strips must ensure that the strips inserted into the ground do not twist when extending plastic drainage strips. A connection method with internal filter membrane and a flat overlap should be used, with an overlap length greater than 200 mm. During the surcharge preloading process, vertical deformation, horizontal displacement of edge piles, and pore water pressure should be monitored, and the loading rate controlled according to the monitoring data. The second method is vacuum preloading. Vacuum preloading is carried out on soft soil foundations by first laying a sand cushion and installing vertical drainage wells, then covering the area with an airtight membrane to isolate it from the atmosphere. The edges of the membrane are buried in the soil. Through the embedded vertical drainage wells, a vacuum system is used to extract air. Air extraction creates negative pressure in the surface sand cushion and the drainage wells, producing a pressure difference between the soil and the drainage wells. Under this pressure difference, pore water in the soil beneath the preloading zone is continuously discharged through the drainage wells, leading to soil consolidation. Vacuum preloading and dewatering preloading consolidate soil by drainage under negative excess hydrostatic pressure, also called negative pressure consolidation. Depending on the type of vertical drainage, vacuum preloading can be divided into ordinary sand wells, sandbag wells, and plastic drainage strips. Key construction points include: 1. Use a jet vacuum pump capable of generating at least 95 kilopascals of vacuum during idle pumping. The number and the placement of pumps should be determined based on preloading area, shape, pump efficiency, and experience, with at least 2 pumps per preloading zone. 2. Vacuum pipelines must be strictly sealed with check valves and shut-off valves installed, and horizontal distribution drains arranged in strip, cone, or feather patterns. The drainage pipes should be arranged in a loop and installed within the sand cushion, with a sand layer of 100 to 200 mm thickness placed on top. They can be steel or plastic pipes wrapped with nylon mesh or other filtering material. 3. The sealing membrane should be made of impermeable material with good aging resistance, high toughness, and strong puncture resistance. During heat sealing, double parallel seams should be used with an overlap width greater than 15 mm. The sealing membrane should ideally be laid in 3 layers, and its edges can be sealed using methods such as burying the membrane in trenches, laying it flat and covering the edges with clay, folding it into surrounding trenches, or applying water on top of the membrane. 4. When applying vacuum combined surcharge preloading, vacuum pumping should be carried out first. Once the vacuum pressure reaches the design requirement and stabilizes, surcharge loading is applied and vacuum pumping is continued thereafter. Geotextiles or other protective materials are used on the membrane during loading. Quality inspection and monitoring during construction include: 1. On-site random sampling of plastic drainage strips for laboratory testing of longitudinal flow rate, tensile strength of the composite, and filter membrane permeability coefficient, and the equivalent pore size. 2. Sampling sand from different sources for particle analysis and permeability tests. 3. For important projects where stability against sliding is a control factor, representative points should be selected within the preloading area for reserved boreholes, and at different loading stages, in situ crossboard, shear tests, and soil sampling for laboratory geotechnical tests should be conducted. 4. For preloading projects, monitoring should include the foundation's vertical deformation, lateral displacement, and pore water pressure. 5. For vacuum preloading projects, in addition to monitoring foundation deformation and pore water pressure, measurements of vacuum pressure beneath the membrane and the groundwater levels are also required. Second, completion and acceptance of preloading. The following aspects should be paid attention to. 1. The stressed soil layers. within the drainage well treatment depth and below the well bottom must undergo preloading with the resulting vertical deformation and the average degree of consolidation meeting design requirements. 2. In situ crossboard shear tests and laboratory geotechnical tests of the preloaded foundation soil should be performed. And if necessary, field load tests should be conducted at no fewer than 3 points. That concludes today's content. This lesson focused on the drainage consolidation preloading method. The key points to master are the definition of drainage consolidation preloading, distinguishing between surcharge preloading and vacuum preloading, and understanding the construction essentials of drainage consolidation preloading. This concludes the lesson. Goodbye.